Welcome to the videos of the 10th chapter of the Crystal Clear Electronics 2 curriculum. In this chapter, we will continue to learn about different communication channels, including serial data transmission. In chapter 8, you already learned about I2C and SPI protocols, and now we will continue with UART, CAN, and USB connections. We will also examine their uses. We are here with the presenter of this video, Ádám Szabó, a mechatronics engineer. He develops custom circuits and prototype systems and is a co-author of the Crystal Clear Electronics curriculum.
Welcome everyone. Balázs Kalincsák, a student at Bolyai János High School in Szombathely, will be assisting me with the videos. As Balázs mentioned, we will be discussing communication protocols. We have already learned about I2C and SPI, which are synchronous communication methods that allow data transfer over small distances, typically just a few centimeters on a circuit board. Today, we will cover UART, CAN, and USB, which operate asynchronously and can transmit data over distances of several meters. While all the acronyms and technical terms can seem a bit overwhelming at first, don't worry, we will go through everything in detail with examples so that everything will be clear by the end of the videos.
That's right. Of course, we also have a practical example. We will create a little drawing game with two microcontrollers using UART communication, and also show you how to use a development board as a USB mouse.
Join us! Let's go over to the table and get started! If you have already studied the Crystal Clear Electronics 1 curriculum, you may have met UART communication in Chapter 18. Here, we are going to go over everything about UART in more detail. We will cover all the details, so it's not worth skipping this part either.
The serial ports we have seen so far, I2C and SPI, exchange information synchronously using a common clock signal. Well, this is about to change. All the protocols we are going to show you are asynchronous. But what does that mean?
Between the devices, there is no clock line or external factor to align the internal clocks of the devices. Consequently, they will need some method to accomplish this between themselves. One more key difference is how data flows. In synchronous communication, data transfer is continuous and happens at a fixed clock rate, meaning it must occur in sync with the clock. In contrast, asynchronous communication allows devices to communicate at their own pace whenever they choose. This type of communication can happen in fragments, and there are no strict time constraints. Both the transmitting and receiving parties use their own clock signals to schedule communication. They achieve a uniform timing of the communication channel by adjusting the clock of the receiving party at different intervals. The roles of the sender and receiver may change or be interchanged, but the internal clock of the receiver is always synchronized to the rhythm of the message sent by the sender, so to the sender's clock signal. The internal clocks of the devices will never match, so there is always some mismatch in asynchronous communication. It is up to the communication protocol what percentage difference it can tolerate between the clocks of the devices.
Can you provide an everyday example to help us understand this better?
Let's see. Imagine a big hall, music playing, and everyone dancing together. If you want to dance with someone, the music coming from the speakers gives you both the rhythm. It's like a synchronous communication. The beat of the music sets the standard clock signal, and people dance in sync with each other. Now, imagine the same room, but everyone has headphones. Everyone dances, but to their own music and their own rhythm. If you want to join in someone's dance, if you're going to dance with them, you have to pick up their rhythm. That is, you have to synchronize with their clock signal. To do that, it is essential to know what music they're listening to and that you two listen to the same music.
I think I understand. Translating this into the world of electronics, in asynchronous communications, it is particularly important that the various parameters of the communication are predefined in each device and that all devices follow the same rules in order to communicate correctly.
That is exactly right. We will refer to the forms of communication described as protocols and standards several times, but these words also have additional meanings. Each of the serial ports in the chapter are built upon and complemented by many other higher-level, more complex protocols or standards. Examples include Modbus RTU, which is based on UART, and CAN Open, which is based on the CAN bus. Let's get started with UART communication. The meaning of the abbreviation is Universal Asynchronous Receiver Transmitter, and it is a protocol defining a communication data link layer. UART itself is the name for the circuit peripheral that handles asynchronous serial communication, but nowadays it is also used to describe the form of data sent during communication. Usually, 2 to 4 signals are used to implement the communication, as shown in this table. The TX leg of one device is connected to the RX leg of the other device, and vice versa. So, data flows on separate wires in one and in the other direction.
And what are the other two signals, CTS and RTS?
Great question! These lines are optional and not strictly necessary for full communication. They implement a so-called flow control to ensure that all messages are transmitted at the right time. The sender uses the ready-to-send signal to indicate that it wants to transmit data to the other device, allowing the recipient to prepare for reception. The receiver responds on the clear-to-send line, confirming it is ready to receive the message. This exchange ensures that data is transmitted only when the receiving party is prepared, preventing data loss and avoiding the risk of overloading the recipient.
So is it like when I address someone and wait for them to look at me, indicating that they are listening? Like when I say, Adam, Adam!
Sorry, I wasn't listening. Could you repeat that?
I was just trying to find a simple analogy for the importance of the RTS and CTS signals. So is it like a handshake? The sender extends his hand and waits for the receiver to return the handshake, ensuring the receiver participates in the communication.
Exactly. The technical term for this is handshaking. Or, for example, it's like addressing people. Hey Balázs!
Yes?
Like this, for example. Why do you think it is not always necessary to use these signals?
I would think that if you send messages rarely, you can assume that the receiver can handle all of them. For example, if the main function of a device is just to receive messages, then there is no need to notify it specifically. Or perhaps it is not even necessary if the message is of such a type that it is not a problem if not all of it arrives completely.
You described it very well. However, it is essential to use flow control signals when our devices have little computing capacity or memory for the number of messages, or when we want to implement high-speed communication. When we talk about UART communication, it depends very much on the circumstances of its use and what exactly we mean. In the case of embedded devices, we usually use point-to-point topology, TTL voltage levels, and positive logic for communication between modules. A large number of microprogrammable devices contain the necessary peripherals.
And what other types of UART communication are available?
For example, there are the RS-232 and RS-485 standards. It is important to note that these basically define the physical layer of communication. There are several layers to a given communication. The two most basic are the physical layer and the logical layer, also known as the data link layer. The physical layer defines the specific physical design of the communication, such as the type of connectors, pin assignments, number of wires, cable design, signal voltage levels, and data rate. It describes how signals are transmitted from one device to another.
The data link layer describes how to convert data into physical signals and vice versa, how to interpret electrical signals as data. Examples of such features are the timing of communication, data framing, and the order of the bits. You can even use different algorithms to detect errors in the physical signal and try to correct them.
For example, the RS-232 physical layer was introduced in the 1960s. In it, it was described that the logical 1 level must be between -15 and -3 volts, the logical 0 level must be between +3 and +15 volts, and only 2 devices can be involved in the communication, meaning it is a point-to-point connection. In addition, only D-sub-9 or D-sub-25 connectors can be used. With the specified pin assignment, flow control is mandatory, that is, using CTS and RTS signals, meaning a total of 9 wires are required. In addition, the maximum speed is set at 19,200 bits per second, and at this speed, The maximum cable length can be up to 15 meters. RS-485 came out later, in the 1980s, and allows higher data transfer speeds. For example, it has a maximum speed of 2 megabits per second over 50 meters, eliminates the need for CTS and RTS signals, and more than 2 devices can be connected. The data is not carried by the absolute voltage of the signals, but by the difference between them, which is called differential signaling. So only 3 wires are needed. The type and pin assignment of the connector is not specified.
It is interesting to note that the same UART data packets travel between devices on these two serial communication systems, which have entirely different structures. We've talked about it a lot, but can you finally show us what this UART data packet looks like?
Of course, let's have a look. The image shows how a data frame is sent. Each frame is started with a start bit. Usually, 8 useful data bits are sent in a frame, but it is also possible to send between 5 and 9. Optionally, a parity bit can be added to the message, which extends the binary form of the data to an even or odd number of ones. Thus, we are able to check the correctness of the received data. Finally, the end of the communication is indicated by a stop bit, which can be 1, 1.5, or 2 bits long. All this will be demonstrated in the example code.
I have a few questions about these. Let's start at the beginning. Why does the communication line take a logical value of 1 in an idle state?
The logic level of the idle state is defined in this way because it is possible to detect immediately if the connection is bad or the wire is faulty. The wire is probably broken if a logic 0 is read continuously for a long time.
This is reasonably practical, but why can we only send 8 to 9 data bits in such a frame? That seems pretty small.
When this protocol was developed in the 1960s and 1970s, the primary goal was to make it compatible with the serial communications that were prevalent at the time and to make it easy to switch over. This is one of the reasons why it supports the 5-bit format used by teleprinters at the time. It also had to consider that because the communication is asynchronous, the clock speeds of the transmitter and receiver units differ to a greater or lesser extent. The shorter the message, the lower the chance the different clock rates would cause a 1-bit time error. For a 10-bit data string, the theoretical maximum clock deviation is 1/10 or 10%, while for a 100-bit data transmission, the tolerance would be 1/100th or 1%. The 8-bit or 1-byte format met all the needs of the time, and over the years, it became the industry standard and is still a very usable format today.
I'm beginning to feel that we could go on forever with the analysis of UART here. Earlier you mentioned that there is no common clock signal, so some sort of synchronization mechanism is needed. Just tell me, where exactly is this happening here?
That's a great question. Basically, the start bit does this. It signals the start of the data package to the receiver, it synchronizes its clock to it, and from here, it starts receiving the 8 data bits. After the data, the stop bit signals the end of the communication and gives the receiver time before the following message.
Now that we know the form of sending data, let's see what else is needed to get two devices to interact. First, we need to set the speed of the communication, known as the baud rate, on both devices, right?
Yes. The baud rate is the rate that determines how many symbols are transmitted per second. In this case, it's easy to calculate what that number is, since in UART communication, each bit is one symbol, that is, a baud rate of 9600, in this case, is 9600 bits per second. There are common baud rate settings for UART communication, but it is important to note that at least in theory, any value can be specified if it can be met by the device. For standardized devices, predefined values can be set to ensure proper clock division. At the dawn of telecommunications, 75 bits per second was popular, but today we tend to think of 300 to 600 bits per second as the lower end of the range, but 9600 bits per second is one of the common default settings. The sky's the limit in terms of maximum, but without wishing to be exhaustive, I would like to list some of the more common values. such as 19,200, 115,200, and 921,600 bits per second.
I assume that everything is already in place for communication. We use the same physical layer, set the bit width to 8 bits, turn off the parity bit, set the stop bit to 1, set the baud rate to 9600, and we're ready to exchange information.
Unfortunately, not entirely. We need to know if both devices can meet the timing criteria with the desired parameters. In other words, can the sender send data as fast as the receiver expects, or vice versa? Is 1 or 1.5 stop bits enough to decode the data? In what environment do we plan to use our device? Is it necessary to use a parity bit to detect possible errors caused by external interfering signals? Unfortunately, all these questions need to be answered, otherwise we may be in for some interesting surprises.
Well, yes, of course, but usually devices only allow settings that they can handle, but this can certainly be found in the datasheet of the device, right?
This is as it should be, but it is essential to point out that the presence of a parity bit is not a complete error checking method, and it is not suitable for error correction. If we really need more complex error checking and correction, we must implement it individually in our code.
I see. But now we can move on to the practical example, can't we?
Not yet. We still have one more thing to discuss. Let's have a quick look at it, and then we'll move on to how we can communicate with our microcontroller on UART. The picture shows two different ways of processing the same signal. The upper interpretation assumes a 5-bit baud.code payload with an even parity bit and 2 stop bits, sending the lowest local value bit first. The lower one is a 7-bit ASCII encoding without parity bit with 1 stop bit, assuming the highest local value bit is sent first. It can be seen that one decoding results in H and E characters, while the other results in K and hashtag symbols. So, it is very important to standardize the bit order between the two communicating devices in addition to the frame parameters. Without this, we can run into problems like this and similar problems during communication.
And what happens if the agreement is in place at all levels, but due to some external influence, the receiving party still receives incorrect data?
In this case, an error message may be received from the UART peripheral. The most common are frame and parity errors, the former caused by missing or delayed stop bits, the latter by a faulty parity bit. An overrun error can be detected by the receiving side if a new start bit is received faster than the previous frame was processed by the controller. Underrun or missing data feedback can be expected if there is no data to send, but there is a request to send it. Finally, a special situation is the break condition, which occurs in the case of a longer logic 0 signal, that is, a low voltage level usually caused by a wire break.
Now we know a lot about asynchronous serial communication. What we have said so far is generally true for asynchronous serial communication with most UART peripherals. As we will see later in the microcontroller's I/O configuration, there are many communication protocols that use a variant of UART.
In the automotive industry, this includes the LIN, or Local Interconnect Network, single wire protocol, but even the SIM, Subscriber Identity Module card, in our phones uses a specific UART-based communication.
We have run out of time, but we gained a lot of helpful information. So, in the following video, we will just try out the UART protocol in practice.
I hope no one has been put off by all these theories. Stay tuned for the next video to see and try how UART works in an STM32F4 microcontroller.
Bye!